Percent composition. The percent composition of a compound is the percent by mass of each element in the compound. The mass percent of an element in a compound can be determined by taking the mass of the element and dividing by the mass of the compound and multiplying by 100 to convert to percent. We can do this if we know the actual mass of the compound and the mass of the element. For example, the percentage of carbon is found by taking 3 grams of carbon that are in a 4-gram sample of methane and multiplying by 100 to get the percentage, 75%. However, we can determine the percent composition if we know the formula by first finding the molar mass of the compound and then dividing the total mass of the element in the compound by the molar mass of the compound and multiplying by 100. For example, in ethane, there are 2 atoms of carbon and 6 atoms of hydrogen. The total mass of carbon is 24.02 grams, and the molar mass of ethane is 30.07 grams per mole. This gives 79.88% carbon by mass, or 80.0. Finding empirical formulas. The empirical formula is the formula that shows the lowest whole number ratio of the elements in a compound. For example, the empirical formula for ethane, C2H6, is CH3. When we only know the percent composition of a substance, often all the information we can get, we can only determine the empirical formula. Both of these are ratios. The way to do this is to assume we have a 100-gram sample, which converts the percentages to grams. 79% of 100 grams is 79 grams. Next, we determine the number of moles of the element by dividing by the molar mass of the element. We convert the moles into a mole ratio for the elements in the compound by dividing by the smallest number of moles and convert these to whole numbers if necessary, so that we have the smallest whole number ratio of the numbers of atoms of each element. These numbers become the subscripts in the empirical formula. For example, suppose we want to calculate the empirical formula of para-aminobenzoic acid, which is composed of carbon, hydrogen, nitrogen, and oxygen in the percentages that you see. If we assume 100 grams of the compound, we get these masses of each element: 61.31 grams of carbon, 5.14 grams of hydrogen, 10.21 grams of nitrogen, and 23.33 grams of oxygen. Dividing each mass by the molar mass of the element, we get these numbers of moles: 5.105 moles of carbon, 5.09 moles of hydrogen, 0.7288 moles of nitrogen, and 1.456 moles of oxygen. When we divide by the smallest number of moles we found, 0.7288, we get these ratios, which are close enough to whole numbers to round off to whole numbers. So the empirical formula is C7H7NO2. To find the empirical formula, we need two things. First, we need the empirical formula of the compound, and then we need the actual molar mass of the compound. It is also possible to get the molecular formula directly. We will look at how to do this later in the video. The molecular formula must be a whole number multiple of the empirical formula. Since the empirical formula is the lowest whole number ratio, and the molecular formula involves only whole numbers as well, you must have this relationship. The molar mass of the compound must therefore be a whole number multiple of the molar mass of the empirical formula. Let's call the molar mass of the empirical formula EFM, for empirical formula mass, and the molar mass of the compound MM. To find the whole number to multiply the empirical formula by to produce the molecular formula, simply divide the molar mass of the compound by the molar mass of the empirical formula. The result must be very close to a whole number. Then multiply the subscripts in the empirical formula by this number to get the molecular formula. For example, if a compound has an empirical formula of CH2O and a molar mass of 90.0 grams per mole, the EFM is 12 plus 2 times 1 plus 16 equals 30 grams per empirical formula. We divide the molar mass by the empirical formula mass to get 3. So we multiply the empirical formula subscripts by 3 to get the molecular formula C3H6O3. Suppose you know that the molar mass of a compound is 62.1 grams per mole, and that the compound is 38.7% carbon, 9.74% hydrogen, and 51.6% oxygen. One could find the empirical formula from the percent composition and use the method we just outlined to find the molecular formula. Using this method, we would get the following moles for each element: 3.222 moles of carbon, 9.62 moles for hydrogen, and 3.225 moles for oxygen. When we divide by the smallest, 3.222, we get 1 mole of carbon, 2.99 moles of hydrogen, and 1.00 moles of oxygen. These numbers all round to the whole numbers 1 and 3 and 1. So the empirical formula is CH3O. This has a molar mass of 31.03 grams per empirical formula. When we divide the given molar mass, 62.1 grams per mole, by this number, we get 2.00, which is 2. So the molecular formula is C2H6O2. An alternate method is possible if we know the percent composition and the molar mass. Instead of taking the percentage of 100 grams to find the mass of each element, take the percentage of the molar mass of the compound. To do this, change the percentages to decimal form, then for each element, multiply its decimal form by the molar mass. This gives us the actual mass of that element in 1 mole of the compound. In this case, we get 0.387 times 62.1 equals 24.03 grams of carbon, 0.0794 times 62.1 equals 6.02 grams of hydrogen, and 0.516 times 62.1 equals 32.04 grams of oxygen. If we divide the number of grams by the molar mass of the element, we must get a number very close to a whole number. These whole numbers for each element are the subscripts for the molecular formula. In this case, we get the following: 2 moles of carbon, 6 moles of hydrogen, 2 moles of oxygen, giving a molecular formula of C2H6O2 and an empirical formula of CH3O. Try this problem using either approach and confirm that you get the correct answers. You may pause the video here until you have solved the problem, or you may wait for the answers to appear and pause the video while you write the problem and the answers and confirm it later.